All right, now that we know how to find the vertex, we want to be able to graph. So the whole point of finding a vertex is to help the graph. So the first thing we have to do here is find the vertex. And before we can find that, which is the middle point, so our vertex is going to wind up going right smack dab in the middle of our table. We need to find the x-intercepts first to help us find that center point of the vertex. All right, we're going to put our x-intercepts here. All right, and that's going to allow us to get enough points to see the shape, but also see the symmetry in the graph. All right, so I got to find the x-intercepts first. Well, x-intercepts occur when the output is 0. So if we're trying to see when x minus 4 and x plus 2 equals 0, well, I'm getting the product of something to be 0. I can think of any combination in the world. One of them would have to be 0, 1,000,000 and 0, 9 and 0, 10 and 0. One of them has to be 0. So if I look at each case separately, if x minus 4 is 0, well, then x has to equal 4. So one possibility is x is 4. That gives me an output of 0. Or if I look at the case where x plus 2 gives me 0, right, in order to make that equation 0, or that statement 0, I'd have to plug in -2. So -2, 0 would be my other x-intercept. All right, this is to help us find the vertex. Well, the vertex is halfway in between these two inputs, and we know that just based on the shape of the parabola. There's symmetry about the vertex. So I have to find the number that's the average of 4 and -2. The way you find an average is you add the numbers together, divide by how many there are. There's only 2 numbers, so I'm dividing by 2. So 4 plus -2 is 2. 2 divided by 2 is equal to 1. All right, and that's because the number 1 is 3 spaces away from 4 and 3 spaces away in the other direction from -2. All right, now we would still need the output for 1, and we also have to pick our other inputs. Our other inputs, we're just going to pick whole numbers around there. And usually we pick it from the same distance from 1. So maybe I just go 1 away. So I have 1 up, 1 down. So we got 0. Maybe go 1 away from these x-intercepts. So -3 and 5. All right, and then we are evaluating at those points. All right, we can choose the inputs in the second table to be the same thing, or really anything. It's a constant function. All our outputs are going to be 7. So now if I'm plugging in 5, so if I replace x with 5, I have 5 minus 4 times 5 plus 2. 5 minus 4 is 1. 5 plus 2 is 7. So 1 times 7, which is 7. All right, and I can keep reiterating this process where I'm just plugging in the new numbers. All right, so if I'm plugging in 2, well, I have 2 minus 4 and 2 plus 2. Well, 2 minus 4 is -2. 2 plus 2 is 4. Right, and so -2 times 4 is -8. All right, and that makes sense. I mean, it seems like a big jump, but I went from 7 down to 0. I'm going down to 8. I should go even lower at my vertex, and then I should start coming back up the same way. All right, so if I plug in 1, all right, and we talked about in the last tutorial that when you're finding the vertex, you'll notice that the outputs actually wind up having the same number repeating in factored form. So when I plug in 1, well, what happens is I get -3, and I get +3, and -3 times +3 is -9. So you wind up getting, a perfect square at the vertex a lot of times with the way these problems are being selected. All right, since these are picked the same, these 2 remaining boxes should be the same, but just to be sure of it, I'm going to still plug those in just to show that they still evaluate the same way. So if I plug in 0, well, that just goes away. I have -4 times +2. That gives me -8. All right, if I plug in -3, well, -3 minus 4 is -7. Negative 3 plus 2 is negative 1. Negative 7 times negative 1 is also positive 7. All right, from here, you're just plotting points to get the parabola. So I have 0, negative 8, 1, negative 9. All right, we have negative 2, 0. We have 4, 0. All right, we're still missing this one on this side, so we have 2, negative 8. We have negative 3, positive 7. So 10, 9, 8, 7. The same height, but at 5. All right, and this lets me see we got our x-intercept, we got our vertex that's halfway in between. We got points that are at the same level, some that are between the x-intercepts and vertex, and some that are after the x-intercepts. All right, and then I'm just trying to draw a relatively smooth curve. I'm using a mouse, so mine's not super pretty, but I have that U-shaped parabola. All right. The other curve that we're looking at is simply the constant at 7. All right, so I can pick any input. Easiest thing to do is generally just pick the same inputs that you used in the other table, since it's not going to affect a constant function. So that way we're putting points at the same spots as we did for the parabola. All right, and since you're just plugging a number in and basically getting out 7, well, that's going to be 7. This is 7. This is 7. All right, there's 7 all the way down. So now when I'm graphing that, well, right, everywhere that I have a point, really I'm just going to have it at 7. Right, negative 2, 7. 0, 7. 1, 7. 2, 7. 5, 7. And we can see our 2 intersection points. I'm going to draw this line in real quick. We see our 2 intersection points are right here. Oh, don't know that. Right here at 5, 7. And we have one at negative 3, 7. And the last thing we're going to do is we're going to solve this algebraically. And we should see that we get the x values of negative 3 and positive 5. All right, so we can see them in the table. Get my highlighter back out. All right. We're seeing the same solutions of 5, 7 and negative 3, 7. All right, which are matching up with these intersection points. The last thing we're going to do is try to get those same x values by doing algebraically. So I'm going to go down to the bottom. I'm just going to set f of x equal to g of x, because that's what intersection points are. It's where the two functions are equal. So if I'm looking when f is equal to g, all right, well, f of x is, we'll scroll up to the top real quick, x minus 4 times x plus 2. I'm just replacing that. That's x minus 4 times x plus 2. And g of x is just the number 7. So that equals 7. All right. Now, when we have two numbers with a product of 7, there's no way to know exactly what the solution would be, right? Because it could be 7 and 1, but it could also be 2 and 3 1/2, 3 and 2 1/3. There's an infinite number of combinations that can produce the number 7. So we really want this right side to be the number 0. I can't really do that from the start, because if I subtract 7 from both sides, this is in factored form. So our very first thing to do is going to be to distribute. So we're going to distribute from factored form to get standard form. So I do x times x, I get x squared. I do x times 2, so I get plus 2x. I do negative 4 times x, so I get minus 4x. And I do negative 4 times 2, and I get minus 8. This is still set equal to 7. All right, middle two terms have an x in common, so we can combine the like terms in the middle. So I get x squared minus 2x minus 8 equals 7. All right. We already said that we want the right side to equal 0 because 0 limits the number of combinations we have. It's either one is 0 or the other one is 0. So I'm going to subtract 7 from both sides. And I get x squared minus 2x minus 15 is equal to 0. But I don't want to have to guess and check in this form, so I'm going to now take this new equation and try to get it to factor form. So if we look at the relationship from factor form to standard form is, well, this third number, this negative 8, and I'll get the highlighter out real quick. Right, so negative 8 here, right, that's negative 4 times 2. Whereas negative 2 is those two numbers added together. It's 2 plus the negative 4. So that means if I look here, I want two numbers that add. All right, so I'll color code it. We're going to add to negative 2. But we're going to multiply to negative 15. I guess yellow is probably a bad color to write in, so we'll just write that one in black. All right, so they're going to multiply to negative 15. All right, now there's a lot of numbers that multiply or add to negative 2. 0, negative 2. 1 minus 3. 2 minus 4. 5 minus 7. There's an infinite amount of things that add to negative 2. There's only so many pairs of numbers that multiply to negative 15, so we're going to list all the possibilities that multiply to negative 15. And that can help us narrow down this process really quickly. All right, and they're trying to add to a negative, so I'm going to have my negatives be the larger column. We have 1 and negative 15. Do those add to negative 2? No. 2 and, that's not going to be a whole number, so I don't have to do 2 and 7.5. I can do 3 and negative 5. Do those add to negative 2? Yes, they do. If I didn't see it, I could complete the list and get 5 and negative 3, but that would be positive 2. And I would get 15 and negative 1. That's positive 14. So the pair that works is 3 and negative 5 because it adds to negative 2 and it multiplies to negative 15. All right, so we're almost done. So we got our factors. These are not our answers. These are just in factored form. I got x plus 3 times x minus 5, and that equals 0. All right, so that means that either x plus 3 is 0 or x minus 5 is 0, which means that if x plus 3 is 0, then x equals negative 3. All right, that's one option. Or x minus 5 is 0. And if that's true, then x must be 5. So we have two possible intersection points, either when x is negative 3 or when x is 5. And if you could remember long enough, these are the same x values that already occurred in our, I need to make a z. All right, they already occurred in our table. So we can see, right, x is negative 3 here, x is 5. So now we've not only done it correctly, but we can see it's the same number in the table as it is algebraically, as it is graphically. So it's a good self-check to be able to do it in 3 different ways. All right.